We're getting ready to move on to the next section of the alcohol lectures, but if you notice, the title is Alcohols and Ethers and Epoxides and Amines and Sulfurs, and we've just got finished with alcohols, and that's it. So look at all of the other sections that are headed my way, and in this video, we're going to talk about ethers. That's the next step, that's the next section, and we need to familiarize ourselves with the ether functional group and how these things are going to react. Now, here's the good news. It's not as going to be detailed as the alcohol section just was. You're going to find out that ethers are very low maintenance. There's very little things that we have to talk about ethers, and I'll explain why in just a second. But here's where we left off, and we were talking about ethers, and we said that these ethers had ROR group, and that oxygen is going to be the site of reaction, just like the alcohols were. When we protonate this oxygen, we're going to have to make a decision on how this oxygen cleaves, because remember, we have a carbon to this side and probably a carbon to that side. So which side would that oxygen prefer to go to and leave behind the rest of the molecule? This is something that we're going to have to be able to pick out and determine in order to predict the proper products for these reactions. So, just like before, we have to protonate it, and protonate it, we got to give it a black eye. Bam! We got to hit it. We got to make it ugly, and by making it ugly, we turn it into a very good leaving group. All right, so one of the reasons that they group these two things together, they do have the same type of mechanism, okay? You hit it, you give it a black eye, you make it ugly, it leaves. However, the Pka values, let's do a quick review of what Pka was. This was a chemistry 251, but really a chemistry 152, general chemistry 2 topic. And a Pka value is the pH at which the molecule loses the proton. In simple terms, that's exactly what Pka is supposed to be. All right, so pKa's for alcohols and ethers, folks, they're 15.5 and 15.7. Look at how darn close those two things are. So pKa has a lot to do with acid and base. So having a pKa of 15.5 and 15.7, these values are very high. What this means is that if I take a little low alcohol and I put it into solution, or a little low ether and I put it into solution, okay, in a beaker it goes, and I have a solution of it, and I start looking at the pH of that solution. Well, let's say that it's very acidic in the beginning. Well, these alcohols, OHs, and these ethers, RORs, will stay intact. That's the definition. So if I increase the pH and I bring it maybe pH to 2 to pH of 7, nothing really happens. I take it to pH of 8, nothing happens. I take it to pH of 10, nothing happens. I take it to pH of 13, nothing happens. I take it to pH of 15, and I'm getting closer, but still nothing happens. And then I take it to pH of 16. What this does is that the alcohols and the ethers begin to act as acids, but only at that pH level, which means that the alcohols and the ethers are very strong bases. And I would know that by simply looking at the Pka value. These values are extremely high compared to some of the other things that we've worked with. And by definition, they are a base. They are a strong base, which means they're going to get what they want. And this was the whole prettiness of these molecules that come in with substitution reactions. It's all related to how good of a base it's actually going to be. So because they're strong bases, they make very poor leaving groups. However, I can get these to be ugly. I can give these a black eye by adding protons to these molecules. They're bases, aren't they? Bases, by definition, accept protons. If I give this thing a proton and that OH now grabs another hydrogen, we now have a leaving group of water that has a different pKa value. It makes it a better leaving group. That's why these things are working. The same thing's going to happen with ethers. If I give proton to the ether and it eats it up, then this ether group is going to turn into a much better leaving group. And the reason is because this piece now is really kind of like an alcohol that's leaving, but there's more to the story than just that. So it is protonated. I've given it a black eye. It's uglier. Because it's uglier, the molecule's more willing to get rid of it. And if it's willing to get rid of it, then it makes it a very good leaving group because of that. The other thing that plays into factor here is that when I do protonate these things, folks, these things are ending up with positive charges. So this is the other part of the story that I'm kind of leaving off. Not only are you giving it a black eye with the hydrogen, but that positive piece has also thrown that oxygen into a downward spiral. And it wants to fix that charge. It does not like that charge to be behind. So it knows at this point, I'm going to have to get rid of a bond. I'm going to have to figure out which bond to get rid of. So protonation is the key. Now, how do we protonate the alcohols? Do you remember? I hope you did, because that was kind of the last section. I mean, we spent video on video on video on protonating an alcohol. Okay, so when we protonate alcohols, one of the first things that we did was add things like HCl or HBr or HI. These were acids. Because they were acids, they were able to donate that proton, and that proton could go onto the molecule and begin to cause these positive charges, which makes these a very good leaving group. So is the same thing here? And the answer is yes. It's really the same thing. So I can take an ether and I can react it with one of these acids, and I can get protonation to happen, and we can initiate a reaction with what was a very poor leaving group. Now it's turned into a good leaving group, and it will leave because I've protonated it. Now, here's the thing. HCl, HBr, HI, we could use all of these for alcohols. I mean, that wasn't anything special. We didn't really target one acid over the other. We said that HBr out of the few was kind of the common, just because HCl, sometimes out of the halogens, that one is the prettiest of the halogen groups, so we might have some complications with those. And then we said iodine was just too large and too fat to go on reliably onto these molecules when they happen. So in this scenario, ethers are slightly different. Okay, ethers, it's not a water molecule that's leaving. This is actually an alcohol group that's leaving. If you look, that oxygen's going to grab an H, and that OH group is going to leave with a carbon remaining group, right? That's what the R stands for. So we're going to be generating alcohols in these reactions. So there is a complication here, and the complication is HCl. This is really too poor of a nucleophile in order to act on the ethers, which means that out of the ugly halogens, yeah, that chlorine is ugly. That chlorine can contribute to this reaction and initiate it, like in the alcohol level. But these are ethers. They're a little different. They might need something a little bit better as far as a future leaving group goes. So HBr and HI. That HBr, that H is going to freely be given up. Bromine can stay behind with that negative, not a problem. HI, that hydrogen can be given up, and the iodine can stay behind with that negative. That's not a problem. HCl, a little different story. It's too poor of a nucleophile in order to add on. It is the least ugly of all of the ugly halogens that's inside of that group. So this is one of the reasons that we never really use hydrochloric acid in these reactions. It's also another reason that in the alcohol section, we use something like HBr very often, because HBr will work with alcohols, and HBr will also work with ethers. HI will also work with ethers. However, HBr just seems to be the most common that people will gravitate to, that will have in their laboratory, and that we can initiate these reactions with. So HBr works for both. You're always safe with it so far. HCl, not so much. Hydrochloric is used for alcohols. It's not used for ethers. We need something a little bit better as far as a nucleophile goes. Okay, so let's take a look at how this reaction initiates and maybe look at the mechanism a little bit before we start dabbling into the example problems. So let's say we have an ether, ROR. Okay, so here's the oxygen. And on one side of the oxygen, let's say that we have a methyl group, so CH3. On the other side of the oxygen, here we have a carbon, and I'm going to turn this into a tertiary carbon just so I can talk about some differences here. So here we go. There's a tert-butyl group. Now, before we go any further, I want to review ether nomenclature because this is something that you should have had in Organic Chemistry 1, and I don't want to take too many things for granted. And maybe if you had Chemistry 251 with me, you forgot how to name ethers. So how do we do this? Well, two processes. A common name and an IUPAC name will come around. So let's talk about the common name first. It's really what's used for ethers. I know, IUPAC is the way to go, but as far as IUPAC goes, sometimes people think that this is a little too complicated, and ethers are more known by their common names anyway. So this is how we do a common name for an ether group. I'm going to look at this oxygen, and I'm going to call this the ether. All right, so I know ether is going to be part of the name. So there we are. And then I name the two groups on either side of that oxygen. So on this side, I have a carbon, and this carbon is a methyl. That's how we would name that normally. And over on the left-hand side, this is a 4-carbon system, and this is a tertiary carbon. So a total of 4 carbons. I need to assign it a common name if I can, and I can in this case. So 4 carbons in total. This is a tertiary carbon, so we call this a tert-butyl group. Now, I put this in alphabetical order, but I do not include T. I look at the B for butyl. If you get them switched, I'm not going to count them wrong. I'm not that picky, all right? So we're going to call this tert-butyl methyl ether. Now, this does have a common name or an abbreviation that it goes by. It's a little strange, though. This is going to be called MTBE. That's the abbreviation that this is known. MTBE. E, of course, stands for ether. M stands for methyl. And TB stands for tert-butyl. Now, why did they put M first if M doesn't go alphabetically first? The reason is because TBME looks a little stranger than MTBE, and that's just the way that they wrote the abbreviation. That's how it's became known as over the years. So there's the maybe first point of confusion with the abbreviation and the common name that happens with this ether group. Now let's talk about IUPAC. How would we name this IUPAC? Well, what we do is we find the longest carbon chain. So the longest carbon chain here is a 3-carbon system. That's the longest continuous chain. So this longest continuous chain is called a propane because there's 3 of them, right? And then on carbon number 2, no matter which way I name that ring or that structure, from the left or from the bottom and up, it's going to happen at the 2nd carbon. So on the 2nd carbon, I have a methyl group, and I can see that up there at the top. And on the 2nd carbon, I also now have this group that I need to name. So this CH3 group, just like before, it's called methyl. And then this OCH3 group, how do we name that? Do you remember? Well, if you don't, you name the longest carbon chain on that ether, which is just 1 carbon here. So this is a meth. And then the O will be represented with the term oxy. So this is methoxy. If it was 2 carbons, it would be ethoxy. If it was 3 carbons, it would be propoxy. If it was 4 carbons, it would be butoxy. Get it? So now we need to put the two together. We have methyl, and then we have methoxy. So metho, methy. So if I want to do this proper, I would do 2-methoxy, and then 2 again, because I have another group, and that is a methyl. So 2-methoxy, 2-methylpropane. So I'm going to react this ether, tert-butyl methyl ether, also known as MTBE, also known as 2-methoxy, 2-methylpropane. Whichever one floats your boat. I don't really care. So I'm going to clear this off, and I'm going to react this ether with an acid. And we want to follow through with the mechanism just so we can kind of understand what happens in these steps. All right, so here's the setup. And this time I've used hydroiodic acid, HI. Perfectly fine. I can use it. Not a problem, whatever. I can use HBr here too. You get the same product, except in the very end, I'll put a bromine on it. Or I'll put an iodine on it here. You'll just put a bromine on it there. The mechanism's the same. So curvy arrows. Well, here's an oxygen. It has a set of electrons, 2 of them. This iodine, it's got some electrons as well. There they are. I've already drawn them, but I'll do them in red just so you can focus on them. And we need to draw curvy arrows. So I've brought in an acid. This acid is going to spit off a proton. That proton, if it can find a negative area, would love to make a home there. Opposites attract. The oxygen in this molecule, this is a negative source, right? This is a negative area of that molecule. Partial negative, at least. We have a set of electrons here. Those electrons are negative, and just like before in the other mechanisms, here is a negative area. I'm getting ready to bring something positive in. So that negative area is attracted to the positive. That's just how we've trained ourselves in organic to write these mechanisms down. It's just a procedure. That's all it is. Whether or not it happens that way, that's a different story. But this is the way that we tend to draw mechanisms every single time. We had to put some order to the chaos. And this is how we do it. So I'm going to start off with my negative area. So that's this oxygen here in this molecule. That is a site of reactivity. And as long as I can get something positive, then a reaction's going to happen. So that oxygen's going to be looking around. It's going to go into the bar. And it's going to look around and see who's in here that will be my victim tonight. Who in here can I sweet talk and just basically convince them to come home with me so that way I can take them for everything that they're worth? Oh, gosh. I see it now. What a disaster. So this oxygen's going to walk in and it's going to look at that hydrogen. Ha ha ha. So that oxygen says, hey, hydrogen, I know you're in a relationship, but I think it's time for you to break up. And I think I can give you more than what you're getting now with that iodine. So hydrogen looks at the iodine that it came to the bar with. It came to the club with them, right? Or her. And the problem with iodine is that it is electronegative. It's over on the side with fluorine, toward the bottom a little bit. And iodine is fairly large. Iodine also has a lot of electrons. And just due to the size, it can handle extra electrons without a problem. So this iodine, again, constantly wants and wants and wants and wants. That's the definition of electronegativity. And it sucks all of the electrons away as it can. And this poor little hydrogen's left with nothing. Nothing. Poor thing. That's why iodine is so preferred to kick the hydrogen off. Because it knows that if it can kick the hydrogen off, it can grab these 2 electrons right here and suck them in. And this is why it's a very good acid. That's the definition of an acid, isn't it? It's a proton donor. It wants to get rid of it. Why does it want to get rid of it? Because the iodine is electronegative. The iodine is an electron sucker. And because it sucks and sucks and sucks and takes everything that it has, hydrogen can be kicked off. So that oxygen is going to come into the hydrogen and it's going to say, psst, hey, break on up, come home with me, I can give you a better life. And that hydrogen says, okay, like it always does. So what we end up here with as somewhat of an intermediate, because the reaction's not finished, I just want to show you kind of the midway step here, is that this oxygen now has an attached hydrogen. And now what we have is big O iodine that can take care of themselves. Well, this oxygen has 3 bonds. There's still a set of electrons up here. It makes it a positive charge. The formal charge of this thing is now a positive. It's gained an extra bond. It shouldn't have that extra bond, but it's there. So oxygen says, oh crap. Like normal, oxygen bit off more than what it could chew. This is always the story in organic with oxygen. So now oxygen has 3 bonds and a set of electrons. And it realizes that seeing 2 people at the same time was okay, but seeing 3 people maybe is a little bit much. So oxygen is going to make the decision on what to do in this step. I've got to get rid of a bond. Which one am I going to get rid of? Well, it's going to look at this newly formed hydrogen bond, and it's going to say, you know, I'm an electron sucker as well. I mean, that's the whole point of why I went to the bar. And, you know, I was looking for Mr. or Mrs. Moneybags. So that oxygen's going to say, hydrogen's pretty dumb. You know, I can take the hydrogen or the electrons away from hydrogen all the time. It's not a big deal. I mean, you talk about sucking electrons, hydrogen is not going to put up a fight. It never has and it never will. So they're going to keep oxygen behind for that reason. Very easy to get your way. But now we have 2 carbons for that oxygen to choose from. And in the beginning, they're both carbons. However, we know the rules of organic. We know that carbocation stability is very important. So if carbon's going to make the decision to cleave, he's going to make the decision to say, listen, you know, I'm getting ready to break up here. And I'm going to have to choose a carbon to break up with. Which carbon am I going to break up with? When I do this, I at least want them to feel good when I leave. I don't want them to have like a mental breakdown or anything, right? I'm kind of looking at them in their best interest. So if I have a choice between which carbon to break up with, I need to look at what happens here if I cleave the left-hand bond or if I cleave the right-hand bond. So if I cleave the left-hand bond, this particular carbon, if this is cut and this molecule leaves and leaves that carbon alone, this is a tertiary carbocation that gets formed. And then over here on the right-hand side, this carbon, if this bond cleaves, what is left over here? Well, this is a primary carbocation. So this oxygen's going to make the decision, okay, out of the 2 choices, when I do this and I break up with one of these, I don't want these to go into a crying fit for weeks on end thinking about all the good times that we shared together. And because of that, I'm going to cleave what I think is going to be the most stable. The one that's grown up a little bit more, the one that can handle this breakup a little bit more. And this one, in this particular case, is the left-hand carbon. And that's because that left-hand carbon, folks, is a tertiary carbon. So oxygen says, I'm going to take these electrons over here, and when I take these electrons, suck them, and that cleaves that carbon to oxygen bond. So I now have 2 products. What I have here is a CH3 group with a carbon, a CH3 up on top, a CH3 down below, and a carbocation that has formed. And this oxygen has taken those electrons off. It now has 2 bonds again, which makes it very happy. And I have a CH3 group with an OH that has formed as a product. Now, the issue here is that this has just turned into a leaving group. And that leaving group has left behind a carbocation. That carbocation cannot stay positive. So a substitution reaction is going to basically happen here, right? This leaving group has left. Carbon has not been a cheater. Carbon is seeing one group at a time, basically. So this is leaving out the front door. And once it leaves out the front door, well, it has room now for another relationship. And that relationship is going to come from something negative. And that negative piece is the iodine that was left over from when it protonated that hydrogen in the very first step. So here, finally, to wrap up the mechanism, this iodine is negative. We start the arrow there, and we point it to the positively charged carbon. Once that happens, we get another product that forms, and this is a CH3 with a carbon, my CH3 up above, my CH3 down below, and the iodine that goes on to that carbon. There's your mechanism of the first ether reaction that we have discussed so far in this section. Things to take home. First, this acid is acting just like all the other acids in the alcohols. They're protonating the hydrogen, or they're protonating the O with a hydrogen. The oxygen here in the ether, that oxygen in that ether is acting just like the oxygen in an alcohol. It is the proton acceptor. It gets protonated. That protonated group now is a very good leaving group. That leaves, a substitution reaction happens because this group is getting substituted with another. What type of substitution reaction happened here? Well, let's think about it. This group left completely because we had a tertiary carbon that was left behind. We formed a full carbocation, didn't we? And then that nucleophile came on to that spot. So this is a substitution. It is a nucleophilic substitution because we're using a nucleophile to substitute because it's negative. And that carbon only had a bond. That bond fully broke. And then only until that point, the new one formed. So that carbon only sees one thing at a time in that spot, and that is a Sn1 substitution mechanism. So if there is a difference in the carbons, this is how we determine what groups will split off in the priority that they want, or that they need, or that they can handle. You look at the carbons, you look at the type of carbocation that would form: primary, secondary, tertiary, benzylic, allylic, aryl. All of those were presented in Chemistry 251. So we're going to start looking at these different types of carbocations. We'll see almost every different type. And if there is a clear-cut difference like this, this is how you determine which side these molecules will begin to cleave. All right, so there's your first example. In the next video, we'll continue on with this discussion. We'll keep trucking through. We'll do some more mechanisms first, just so we can understand how these things are going to break and why. And then what if the two carbons are the same? What if we had a secondary on the left and a secondary on the right? Or a primary on the left and a primary on the right? How do we determine what gets split at that point? So we need another rule. We need to kind of remember that when that time comes, because at that point, it's a tie for carbocation stability. So there's got to be something else in the driving seat that will make these decisions for us. And we'll talk about what that is next when we come back.